This is a video lecture on friction in elasto-hydrodynamically lubricated contacts. So, typically found in gearboxes, for example. I'm Roland Larsson. I'm from Luleå University of Technology in Sweden. So, I will simply talk about the losses you can find in EHL, and that's a kind of another type of viscous loss, I would say. Starting with the influence of pressure on viscosity, or reminding you that viscosity changes very much with pressure, at least at low or no shear. Yeah, assume that we have been able to measure this friction or the viscosity, under almost no shear force or shear motion, I mean. Then at low pressure, it's relevant to use what is normally called the Boris equation, which it wasn't really derived by Boris, but it's named Boris equation in the EHL community. Anyway, this equation is simply an exponential equation relating viscosity and pressure, and the parameter alpha is telling you about the slope of this curve. So the higher the number, the bigger the slope in the beginning. It's valid up to a number of hundreds, a few hundred megapascals, and after that it's not really valid. But in lubrication, it seems to be still a good number to use for at least for film thickness, not for friction, which we are going to talk about today. Actually, it's maybe not a very good number, but still I want you to remember this number, alpha. The alpha is varying for different types of lubricants. So naphthenic mineral oils has a pretty high number. Polyalpha olefin, significantly smaller number, and ester even smaller. Smallest of them all of different fluids is alpha for water. It's maybe looks as a small difference here, but this factor 4 difference between the ester and the water makes a big difference when you put it in an exponential expression like this. So the water viscosity hardly increases at 1 gigapascal. So it's just a few times higher viscosity, starting from a low value. I mean, water viscosity is low already from start. At the same pressure, polyalpha olefin may be more or less solid, and the mineral oil is even more solid. So it's more like a glass window. So it's completely different between the water and the oil. So what will the friction be then if the viscosity is something like a million Pascal seconds, as it could be according to this equation? Well, it's easy to make some kind of approximation here. The friction coefficient is of course the shear stress divided by the pressure, the normal load, or the friction force over the normal load, same as shear stress over pressure. And since the shear stress is the viscosity multiplied by the shear strain rate, you can approximate it to viscosity multiplied by the speed difference of the two surfaces divided by the film thickness. Well, the viscosity is then, by using the Boris equation, you can get the pressure dependence here. And finally, you put the expression for the shear stress into the expression for coefficient of friction, and you end up with this one. Then let's put in some numbers here. Typical viscosity, say 0.1 at atmospheric pressure, 0.1 Pascal seconds. A typical alpha, 2 multiplied by 10 to the power minus 8. Typical pressure, 1 gigapascal. And again, pressure 1 gigapascal. Typical film thickness, 1 micrometer. Then you end up with a friction coefficient of 48,500. that's not really a number you expect from a friction coefficient. Normally you expect a number much lower than 1 maybe, especially in a lubricated contact. So something is wrong here. And that is that the viscosity is not at all as high as 10 or 1 million Pascal seconds when you start shearing it. And in this thin film, the film is severely sheared. It's more than typically 100,000 or a million or even 10 million reciprocate seconds of shear rate here in the bearing. And at that shear rate, the apparent viscosity is much lower than at low shear. So it's this is from a relatively recent work by Robbins and co-workers, and here you can see how the viscosity changes with the strain rate, shear strain rate. So it's at low shear you can see here that it's a kind of a exponential increase of the viscosity as we expect from the Boris equation. But when you start shearing it for the low pressure, 0.1 megapascal only, you can shear it up to say 100 million or even 1 billion reciprocate seconds, and there is not much shear thinning of the oil. This is a squalane, it's a kind of a model hydrocarbon. But at higher pressure, like this is 500, 600, 700, 800, 900 megapascal, still a relatively low pressure to be in EHL. You can see that already at 1,000 reciprocate seconds, the apparent viscosity or the real viscosity falls heavily, and at the typical operating shear strain rate, which is say at 1 million or even 10 million reciprocate seconds, the viscosity is now, instead of being 10,000 up here, it's now only 10. So it has fallen 3 orders of magnitude, 1,000 times. So that explains why the friction in a real case, which you may know is in a lubricated contact, is around 0.05 or so. So over the years, we have been measuring the shear stress versus the shear strain rate, and we get a typical curve looking like this. It's a kind of mu-slip curve. So it goes linearly in increase in the beginning because it behaves a little bit like a Newtonian lubricant or Newtonian fluid, but at a certain shear strain rate, you reach a maximum number here. That's when the viscosity, when the shearing becomes so severe, then the shear thinning is also very severe, and actually at the same time the temperature increases in the film, so it reaches a kind of maximum number, and if you keep on increasing the shear strain rate, you simply reduce the stress due to thermal effects. And over the years we have been calling this the limiting shear stress. We are not sure if it's a real physical number, if it's a kind of yield stress of a lubricant, or if it's a thermal effect, simply that you shear it, you heat it up severely, and you reach a kind of a limit of that reason. But you can measure this limit for different lubricants, and normally you see a trend like this, that the typical mineral oils have a higher number than an ester, for example. So the limiting shear stress is simply this gamma number multiplied by the pressure. So this could be said to be an EHL friction coefficient. So if you want to take a number for a certain oil, you can use this table, but it varies very much depending on the operating conditions. So if you measure this in a ball and disc apparatus, you will get a curve looking something like this. Again, linear in the beginning when it behaves more or less like a Newtonian fluid, but it's only for very small slide to roll ratios, very little sliding, very little shearing. very soon it reaches a maximum, and due to thermal effects it reduces even more when you reach, maybe here you have full sliding contact. So if you measure that under different entrainment speed and different slide to roll ratios, different slips, you can create a map like this. And in this map you can see that the friction coefficient varies a lot, from 0.02 something up here in this corner to say 0.065 down here, or even 0.07 down here when you have low speed. That means that you may even have some effects of mixed lubrication here. You can also plot this 3D diagram in 2D. For example, if you follow the red line here, like changing the entrainment speed, you get the Strebeck curve. This is a typical Strebeck curve for a EHL, or elasto-hydrodynamically lubricated contact. It reduces here in the beginning because you get less and less mixed lubrication, and you reach full film somewhere here. And then when you increase the speed more and more, due to thermal effects, you get lower and lower friction. In a journal bearing you have a slightly increasing friction because of viscous losses, but here you get a dominating effect of the thermal effects, and that makes your friction to go down. If you plot in this direction, on the other hand, and you also add, you can change to, this is a positive slide to roll ratio, but you can also change it to negative slide to roll ratio. It simply means that the other surface moves faster than the other one. Then you get a curve that looks something like this, and this is a typical mu slip curve. So you can recognize this shape as I showed you before, and you can get the same but antisymmetric on the other side, in the other direction. So a mapping like this is useful for friction in EHL, but it also tells you that it's not very easy to say one number for the friction coefficient in an EHL contact. So a little bit an important thing here about EHL friction and film thickness is that they are not really connected to each other, because the film thickness is, as you may know, controlled by what is happening here in the inlet. The oil that is trapped here is trapped, and then it can't move anywhere, and it can't escape from here. So what is trapped, and that is also controlling the thickness of the film. But the friction is completely controlled by what is happening inside the contact here. So the lubricant inside here is determined, the properties of the lubricant inside the conjunction is controlling what friction you get. And of that reason, it's very important to learn about the rheology at high pressure and high shear rates. So of course, if you now move the upper surface faster than the lower one, you will shear the almost solid lubricant in here, and when you shear at a high pressure, very high temperatures will occur. So you may have a hot spot somewhere here, and when the temperature goes up, the viscosity will go down, and you may have a low slip plane somewhere in the film. This is a funny effect that you can see sometimes. There is a trend to reduce the viscosity in gearboxes, and that's because you want to lower the splash losses in the gearbox. But in what is happening in the actual gear teeth contact, then, if you have a low viscosity oil and measure the friction at very high pressure, the gigapascal range, you can plot the map for the low viscosity, and you can plot it for the high viscosity. And now you see here that actually the high viscosity lubricant under EHL conditions, the friction coefficient is lower for the high viscosity lubricant. That is maybe not expected, or not even known by most lubrication engineers. So that's important to remember, that the low viscosity oil may get you higher viscosity in the actual EHL contact. Another interesting thing is coatings. And coatings may reduce the friction even in full film lubrication. So normally you use a coating to protect the surface from the other surface. But in full film EHL, we have also shown that it has a great effect on the friction. And this is a little bit unexpected, but it can be explained by thermal effects. So you see here that you have two cases. We can take a look of the experimental curves here. So the dashed curves are the experiments. This is the friction. You recognize the mu slip curve for an uncoated case, and this one is the coated case. So you can see it's significantly smaller friction when you coat the surface, even if the surfaces are not touching each other. So why is it like that? Well, the explanation is that there is a thermal effect involved here. When you put a thin coating, it's very thin, but in this case it's a DLC coating, a diamond-like carbon coating, and this coating has a very poor, in this thin condition, a thin layer, it has a very poor thermal conductivity, and that means that the very good cooling from the metal surfaces is stopped. That means more heat is staying inside the lubricating film, and of that reason you have a kind of thermal softening of the film, or a kind of reduction of the real viscosity inside the film, and of that reason you also get much lower friction. So this is we found out that in just a few years ago, actually. So this is just another reason to coat your surfaces if you want to have an efficient gearbox, for example. There could be other problems with the coated gear teeth, but this could be a benefit of coating it. It's still a research task to explain what is happening inside an EHL contact, but you can definitely conclude that there are thermal effects involved here. When you shear the lubricant film, remember now it's very thin in comparison to its length, but we just plot it in this way to illustrate what is happening here. You can see that when you shear, if one surface is moving faster than the other one, you will have a hotter plane in the middle here, or this is maybe showing you that better. So you will have a hot plane in the middle, and when you have a hot plane, the viscosity will go down, so it will be easier to shear it at that position. And that means that instead of having a couette profile like this, you have a flow profile that looks like this. So all the shear is taking place here in the low viscosity mid plane, while the lubricant follows the upper surface here, and it follows the lower surface here. And so we believe that the thermal effects are very important and lowers the viscosity in the mid plane here, and that's where the shearing takes place, and that is controlling the friction in the EHL contact. So it's the viscosity in this plane that is telling you what the friction will become in the end. But this is still a research task to really explain the friction in full film EHL. A few words also about the alpha, or the pressure viscosity influence. If you have a lubricant with significantly lower alpha, like the water, but water has a very poor, or it's a very low viscosity to start with, but if you have some other fluid that has a low alpha but a high viscosity, one such fluid is glycerol. So this plot shows you the benefits of using glycerol or using a low alpha base fluid. So in this diagram you can see the stars here, that's the rapeseed oil. So it's a kind of natural ester, and that has a relatively low friction here at increasing slide to roll ratios. You have something like 0.35 in friction coefficient for that rapeseed oil, which is a pretty low number to start with. Mineral oil may be up here somewhere. But if you then take the glycerol, if you take the pure glycerol, you end up with a curve here. But if you mix some water in it to get a lower viscosity to start with, you may end up down here typically with some 5, 10, 15% of water. And then you see that the friction coefficient is down to 0.01. So it's 3 times lower friction with the glycerol than with the rapeseed oil. So so if you can keep the film or the surfaces apart, still keep the full film lubrication condition, you may reduce the friction by 3 times by using a low alpha fluid. So that's something to remember too. So is it the low alpha that does the trick? Well, you will see here that the viscosity for a glycerol water at 1 gigapascal is something like 4 pascal seconds, while the viscosity of an oil is something like 2 million pascal seconds. So you see here it's almost a million times difference in viscosity. So that's the reason why you get a much lower friction in that case. So to conclude then, or how to summarize, how to reduce viscous losses? Well, you can do it in different ways. You can reduce the viscosity, but if you do that, you must be aware that you may change the regime. If the viscosity becomes too small, you may end up in mixed lubrication or boundary lubrication. And you must also remember, as I showed, that in EHL, other parameters are important. It's not only the viscosity at atmospheric pressure, it's the viscosity at the operating pressure. And a low viscosity oil may have a higher EHL friction than a higher viscosity oil. You should of course maximize the lubricant film thickness, but if that's tricky if you at the same time tries to lower the viscosity. But a thicker film gives you a lower friction normally, because you remember the expression viscosity multiplied by speed divided by film thickness. So the bigger number, the smaller the friction. If you reduce the oil level, you also reduce viscous losses of some types, the splashing type of viscous losses. That's in a gearbox, for example, the height of the lubricant in the actual gearbox. The lower the level is, the less splashing you have. And you can also select the proper base fluid. So what we normally say when we talk about oils is that synthetic types of base fluids like the polyalpha olefins or synthetic esters are normally better than the mineral oils. But if you want to have a really low EHL friction, you should use water-based fluids because they have so much lower alpha. But then you must be sure that you can keep the full film condition, of course. So that is what I had to say about full film friction in EHL. So thank you very much.